Today we will discuss about invariant reactions. But before going through the invariant reactions, we need to know about the degree of freedom. So to make you better understand the concept of the degree of freedom, look at this diagram very carefully. This is a solid phase and this is the liquid phase at this temperature and this composition. And there is in between this region which contains both the phases, that's liquid and solid, both the phases. So in case of solid here, apply the Gibbs rule formula for the binary phase diagrams. That's given by this formula, as you can see here, F equal to C minus P plus 1. So we can see here that the composition of the solid at this point is 2, because it has two compositions. We know this is of two metals, so composition C is 2, and we will minus it by phase. Phase is only 1, so 2 minus 1 plus 1 is 2 minus 1 is 1 and 1 plus 1 is 2. So there are the degree of freedom at this point is 2. And what does the degree of freedom here means? What do we mean by that the degree of freedom is 2? That we can change the temperature and the composition at this point very easily, and it will not change the change the state of this solid. Now let us go to this region. Here in the liquid plus solid region, there are two phases present. So we will again apply the formula C minus P plus 1. So C is 2 components, P is 2. So 2 minus 2 is 0 and plus 1 is 1. So there is only 1 degree of freedom here. So we can either change the temperature or the composition, but we can't change both at the same time because the degree of freedom is only 1. So I hope that you have understand about the concept of the degree of freedom. Now let us go back to the invariant reactions now. As you can see clearly, it has been written at the introduction that in a binary component C equal to 2 phase diagram, if 3 phases coexist, then the degree of freedom at that point is 0, because the phases present are 3 in the invariant reactions. So we will take an example here. This is a binary eutectic system, and this is a depiction of the lead and tin equilibrium phase diagram. This is a very classic example. Actually, the lead and tin is used in soldering alloy. So this is a soldering alloy, and this is the phase diagram, the binary phase diagram of this. But in case of invariant reactions, we don't have only 2 phases. We have 3 phases. So at the 3 phases, we have 0 degree of freedom, we know. But how there are 3 phases? Now let us please keep concentration. This is the liquid state. When we melt this alloy at this temperature, we go to the liquid state at this temperature and composition. This point of graph, this is liquid state. But when it melts, it starts to melt or it starts to solidify. When the temperature goes down, we reach a point called the eutectic point at 61.9% of lead, and at temperature 183 degree, we can see that there is a point called eutectic point. It's a dip. So the melting point of this point is less than these regions. The liquid is getting at this point, at this eutectic point. So liquid is just one phase, and it is getting converted into the solid, but 2 phases. So these are 2 phases and this is 1 phase. So the phase becomes 3 at this point. So there is 0 degree of freedom. So what it results in? It results in that the degree of freedom 0 means this occur only at a particular temperature and particular composition, and the point in the phase diagram is known as invariant point. Any reaction transformer occurred at that point is termed as invariant reaction, since it occurs under the equilibrium condition at a specific temperature and alloy composition which cannot be varied. Therefore, the temperature and composition cannot be varied. So I hope that you understand the invariant reaction. In the future videos, we'll discuss about the binary eutectic alloy system and peritectic alloy system and all the other stuff. But stay tuned to my channel and subscribe.